Okay, I have here another limit problem on the board. We have the limit as x approaches infinity of x squared times e to the minus x. I got the idea from this because I was working on Laplace transforms, and in that playlist a lot of times we come to, like in an integral, we get to a situation where we have something, I don't know, something like this, that we have to evaluate this from 0 to infinity. And what happens when we do this, if you just distribute in this e minus x, this right here is really the problem we have, is we're evaluating this as a limit as x approaches infinity of x squared times e to the minus x. But oftentimes when we're doing this as an integral, we just kind of do it really quick. We don't formally do out the limit, and so that's why I wanted to do this limit problem today. So to get started with this, let's just see what happens kind of when we plug in infinity. So if we plug infinity in for x squared, this gives me infinity. You plug infinity in, e to the minus x, think of it like 1 over e to the infinity, and that's going to 0. So we end up with this indeterminate form, infinity times 0, and we just don't know what this is without doing some more work. But what I can actually do is if I just rewrite this limit, and we'll keep x squared, but then what I can do is bring e to the minus x into the denominator and write it like this. Well, now we have this fraction where we potentially can use L'Hopital's rule, but let's just confirm. If I plug in again infinity squared, we have infinity here in the numerator, and then we have plugging infinity here, we have infinity in the denominator. You always want to do this check before using L'Hopital's rule, because it's not enough to have an indeterminate form. You have to have one of these indeterminate forms before you can go ahead with it. And so this is going to be our second case, the infinity over infinity. So this is a good case where we can use L'Hopital's rule. And we have our definition for L'Hopital's rule over here on the right that tells us if we have this limit as x approaches a of fx over g of x, and it's one of these indeterminate forms, then we can just take the limit as x approaches a of the derivatives of f over g. So using that, we'll just go ahead. We still want to take the limit as x approaches infinity, but we want the derivative of x squared, which is just 2x, and we want the derivative of e to the x, which is just going to be e to the x. Now, evaluating this at infinity, you plug infinity in, we still get an infinity over infinity situation. So we're in a situation where we can use L'Hopital's rule again because this limit is still an indeterminate form. So then coming down here and just taking this derivative again, still we want the limit as x approaches infinity. We take the derivative of 2x, and we'll have 2 in the numerator. We'll take the derivative of e to the x again, and we have e to the x. And now at this point, you notice this is no longer an indeterminate form. Because we have 2 in the numerator, it doesn't match either of these cases. This is going to be, we can look at this as 2 over infinity. But for 2 over infinity, this limit is just going to be approaching 0. Again, this is really useful with Laplace transforms because then when we have a term that's 0, a whole part of the problem goes away and it helps us simplify it pretty nicely. So that's it. Thanks everyone for watching. Have a good day.